Hi, welcome back to Current Topics in Finance. This is week 6 portion of my lecture. We're going to talk about uncertainty and model selection this week. You know that I've been going through the textbook in a more different manner, so that this week we're going to cover chapter 1 and 3. Okay, there is a reason why I'm doing that. First went through the regression part and then refreshed our memories about your regressions and statistical analysis. We are going this week about the data science part. And this is, all these data science exercise is about statistical testing, by the way. But for finance purpose, why do we care about it? Well, you can think about developing, a machine-based buy, hold, sell mechanism for stocks, right? Based on those data, what deserves buy, what deserves sell recommendation. We're gonna do some. You want to do some kind of a forecasting based on it. Okay. Also, you want to do some kind of a finding risk factors if you are hedge fund managers, right? Some factors in your data may be garbage. Some factors may not be, right? And you may have found some important things over there. How to discriminate this thing is a very important issue. And then if you are hedge fund managers or private equity managers, right? You are more interested in corporate events, right? Event-driven hedge fund is also there. What are those major corporate events? Well, bankruptcy. Well, not only for private equity, but commercial banks and all these rating agencies, right? You care about bankruptcy. How can you better predict bankruptcy is a critically important issue there. Also, if you are, financial regulators and the policemen in the financial market, then you will care about financial fraud, okay? Of course, as an investor as well, private equity managers, you don't want your CEO to be a liar, right? So that's why financial fraud and forensic accounting wise, you need data science. Also, one of the important events in corporate world is mergers and acquisitions. Some companies are more acquisitive to acquire different companies here and there. Some companies are never acquiring anybody. So what is the likelihood? And can we better predict the likelihood of acquisition? Also, if you are a venture company, you want to be acquired by somebody so that you can, sell off your company in expensive ways. And what is your likelihood of getting it, right? That kind of things is a very important thing to statistically predict, right? And then another major event in corporate world is the changing of leadership, the CEO getting fired, okay? Kicked out from the company versus not. Stock price responds to it significantly. Why? Well, those are some of the key people in the corporation. In the end, those are the drivers of your, stock performance in individual stocks, right? You don't want your CEO guys to be crazy guy over there. Has to be fired sometime. But what is a key predictor of doing it? For that part, this statistical test will be an awfully interesting exercise to do it. And I give you those data to you, right? Those data that I preciously hand collected with 몇천만 원, right? So, tens of thousands of dollars I spent. I'm just giving it to you for your development, okay? Don't spread it to any other people, okay? You have to promise me and email me that you're not going to share with anybody. Legally, it's important. You just keep it over there. All these things, by the way. You will like it, I hope, okay? And virtually you can write a master's thesis based on the data that I gave you. Mostly use regressions and finding a valid predictors is equivalent to finding a beta coefficient that is significantly different from 0 using the data. If you think about regression framework, those beta, okay, the coefficients, sensitivity kind of things, right? What are we doing over there? What were we doing? We are trying to find whether this explanatory variable is a significant predictor for the dependent variable or not. Okay, that's why. Those testing, okay, are not just a single variable regression like in CAPM, but multiple regressions, okay? Thousands of, or hundreds of at least, right? Hundreds of explanatory variables, but some or significant part of it are garbages. How do we throw out those things is an issue. Now, agenda, okay, confusion matrix, type 1 error, type 2 error, we're going to talk about that, and false discovery rate, also Benjamini Hochberg algorithm. We're going to talk about these things and concepts and model selection. We'll move down there because Hochberg, Benjamini Hochberg algorithm or FDR, those kind of things are assuming that those explanatory variables are independent of each other, which is not really the case most of the time. Stepwise forward regression will be the first thing you're going to talk about, and then you're going to move on to regularization. There we're going to talk about ridge regression and lasso regression, okay? Which is very, very important in data science. You're going to be tested, okay? Without lasso regression, don't talk about data science, okay? AIC, corrected version, and then BIC. All these things are related to throwing out garbages and choosing the best predictors in data science perspective, okay? Remember, this is data science perspective. What am I talking about? Well, for example, bankruptcy prediction. There are certain key variables the theory predicts, right? The corporate theory of bankruptcy predicts a certain variables are important. In your data, you're going to have some default probability measure called real KMV EDF, which is, you Google search those variables, right? You're going to find that it's going to be a stunningly important variable in default prediction, okay? KMV, go ahead and find out what those are. Essentially, KMV is the one that drove me to study, going to the PhD, going to the financial engineering study and all these kind of things, right? Those variable is given to you over there, unimaginable in my, by the way, those theory-based ones are there, okay? But data science may find out some other variables unintentionally, okay, unexpectedly, okay? Maybe you may be able to find some real important one that was not previously discovered, okay? Maybe what you find is garbage, okay? Let's find the garbage together and let's throw out those garbages, right? That's the approach, okay? Yeah. Testing, when it comes to testing, this is COVID-19 era, okay? So, drive-through testing, all these things are related to statistical testing, okay? Positive versus negative. You have disease or not. Hope everybody is negative if you test any COVID-19, right? Let's stay healthy. But, who is it? Yeah, Donald Trump recently tested positive. He said in a tweet, right, saying, tonight, somebody, Melania, and I tested positive for COVID-19. Shame on you. But he said what? We will begin our quarantine and recovery process immediately. We will get through this together. Together? What do you mean? Come on. No, not me, right? You go there by yourself. Come on. And then, a couple of days later, he was back. He was back. Oh my God. And then not only that, the White House people gets infected thanks to Donnie, yes. And then there we have a handful of questions related to this one. Okay, first of all, was he really infected or lied? Okay, he's a US president, so let's say he, did not tell a lie. If that is the case, then how accurate was the test? Okay? Was there any chance of false positive? And then he gets back without 100% curing the disease. What about the staff in the White House? I told you, right? If Trump recovers, test negative today or tomorrow, or maybe 2 weeks later, how accurate is the test again? Okay, is a serious question. Is there any chance of false negative in this case, right? Stay there. Now, as some staff members gets infected by Donnie, right? What's the chance that Trump gets infected again? Okay, and on and on and on and on, because the White House staff gets infected. It's mutually giving each other back and forth, back and forth. COVID-19 is well known that there is no perfect immunization at all. Good luck, man. Anyway, so start with a single test, okay? A single test, whether you have a disease or not, okay? COVID-19 kind of things, right? We start with a null hypothesis, which null is like coming from German language, right? Null, right? Zero, right? Zero. Null hypothesis. This is our safe bet, okay? That you don't have anything, right? In the CAPM context, right? Testing with some kind of risk factor like a market index, right? And index return. Beta being 0 means like what? This risk factor is nothing, okay? Not an effective risk factor, beta 0. But beta being significant means like what? It's not 0, okay? Significantly affecting your risk, your return, right? Expected return. That kind of thing is going on. So null means nothing, okay? A safe bet, status quo, setting a parameter equal to 0, null, right? And then alternative hypothesis is a set of possible values, right? At least non-zero, okay, kind of things, right? Now, you see on your right-hand side two probability distributions. One on the left-hand side is null distribution, and the other on the right-hand side is alternative distribution of your probability. Let's say your test result for COVID-19 is about your saliva or something like that, right? And then out of it, they dose some chemicals in it, and then maybe they find out some kind of chemical responses, okay? Those frequencies and the density of chemical responses, maybe you can think about a continuous spectrum of those chemical responses, okay? I don't know what that is, but let's say a chemical responses, okay? Maybe the chemical turns out to be more reddish, right? Somehow, okay? It's not like a totally no response versus whole lot of response, right? There may be some continuum of responses. You can think about it that way. So for healthy person, okay, you can think about a probability distribution of this kind of a redness of these chemicals, right? Some people, healthy people, generally they may not have that color or something like that. But for sick people or the infected people, right, they are more likely to develop into reddish, really, really reddish color over there, okay? You can think about a continuous spectrum of that. Some people, right? Some people, healthy people, may also have some kind of a reddish response, even though their, health condition is perfectly fine. Okay. Some people, on the other hand, get infected, and then they're more likely to get wilder response, like red color over their chemical responses over there, right? Of course, they will be more dominantly having thicker colors over there. But the thing is, those infected people may also respond, their chemical response may be weaker over here like this, okay? So there is an area of mixture, okay, where those chemical responses are reasonably there, but it's kind of hard to distinguish whether it is really an infected person versus healthy person like that, okay? We have some confusion over there. We're going to talk about confusion matrix a little later. What you have over here is a true negative and true positive. Okay, true positive means, oh, you got infected. Mr. President, go to hospital. That's it. True negative is like what? You're healthy. Don't worry. False positive is what? You're healthy, but the color, the chemical response says you seem to be, nah, go to hospital. That's false positive. And then false negative is what? Your responses, color response is not there, but you're seriously ill. Okay, this kind of 무증상자 kind of things is there. No symptom COVID-19 patient, no symptom patient. That's kind of this guy. Okay, false negative. Okay, let's move on to the next slide. So here, the confusion matrix is the one that Tim Lung highlighted over there in the Tencent, right? Remember, accuracy of test is one of the most important aspects in machine learning. There, you may think about 2x2 matrix, right? Thinking about COVID-19 kind of things. Having a disease means positive. Having not disease is a negative, which is kind of counterintuitive because the negative means like something bad, but here negative means you're healthy. Okay, actually you're healthy means actual negative. Okay, so there you can think about 2x2 matrix, which is you are actually sick, right? And then the machine says you're sick. That's true positive. Actually you are healthy, but the machine AI says you are sick. That's false positive. Okay, and then actually you're sick, and then the machine says you're healthy. That's false negative. And then actual negative, then the machine says you're healthy as well. That's true negative. By this 2x2 matrix, you can construct two different measures, which is first false rejection rate called alpha, which is false positive divided by the false positive plus true negative, right? So in this over here, out of this big distribution, what is the FP's area? Okay, that's false, what's that? Rejection rate, false rejection rate, FRR. And the other is false acceptance rate, which is false negative divided by false negative plus true positive, which is, if you look at this graph over here, the area of Fn relative to the area of this small bell curve over here. Okay, so that's FAR. And then right, so you can think about it in this kind of a nice picture over here. FAR and FRR looks like this. But the thing is, as you move this threshold bar from left to right or right to left, okay, you will see some kind of a trade-off between FAR and FRR. Okay, okay. The following is about the construction of this. Okay, FAR and FRR. And then the accuracy, right? Accuracy on your horizontal axis, and then the percentage, right, of the rate, FAR versus FRR, as your false rejection rate. Okay, false rejection rate of alpha goes down and down, down and down and down, down, which means you move from right to left. Okay, then you will realize that false acceptance rate will go up and up and up and up, and vice versa. If you go to alpha being higher and higher and higher and higher, right? False rejection rates goes higher and higher and higher. your false acceptance rates goes down and down and down and down. Okay, there's a trade-off like that. Where is the equilibrium, or where is the optimal point? Okay, so that you will be scientifically, okay, accepting and rejecting in a reasonable level is an important issue. And then the trade-off between FAR and FRR in facial recognition was discussed in the previous lecture, right? There, if you want to, how do you say, reduce false acceptance rate, okay? You don't want to accept, okay? You don't want to accept too many people, okay, into your country. Let's say you are visa processing immigration officers, right? And then you want to discriminate out the potential criminals out, okay, by facial recognition or something like that. If you want to reduce your false acceptance rate into your country, what happens? You reject everybody, so many people, okay? 일단은, right? Just first of all, just reject everybody, just to be safe, right? That's what's happening over here. False acceptance rate minimized, but that sacrifices your false rejection rate. So many people will be rejected in the first place, okay? And actually, this is what happened after 9/11 terrorist attack in 2001, okay? All those foreign students, right, applying for visa in the US were first of all rejected. Many of them were rejected falsely, okay? Because the country wanted to be, the US wanted to be safer, okay? And it's nothing to blame, right? On the other hand, if you go down over here, okay, if you don't want to piss off so many people, right, you want to be friendly, then you will reduce your false rejection rate and sacrifice false acceptance rate. You just user friendly and easy to get through. Don't get as much false rejection. That's what's going on over here in this graph. And then what did Tim say? Well, pushing down this curve, trade-off curve, is the job of the machine learning. Okay, so as this technique gets developed and developed and developed further, people may, the curve may go down and push down to, more efficient level. Okay, so that's that. Hypothesis testing, right? You'll remember the p-value, right? Being bigger than a threshold t statistic, right? Absolute value of t, right? And then you must have seen some stars, the significance level and significance representation, statistical significance. What was that about? We're going to talk about it. For test of beta equals 0 versus not, the test statistic is z statistic. Okay, why isn't it t statistic? Because n is big. We are talking about big data, big N. Okay, of course, not just a big N observation. Today we're going to talk also about big number of variables, right? Rows and columns, big columns issue will be there as well. How many standard deviation is our estimate away from 0 or null hypothesis was the issue of this p-value, okay, or t statistic or z statistic. The p-value is then the probability of z, the standard normal distribution statistic, being bigger than a certain threshold z statistic beta hat, z of beta hat, with z being normally distributed, standard normal distribution, which means the mean is what? 0. Standard deviation is what? 1. Unit standard deviation. That's z statistic over here. So what's the chance that you're going to see this kind of beta over here or over there if the null hypothesis of beta being 0 is true? Okay, that is the question we are addressing with this p-value or z statistic. A p-value is a probability of statistical test statistics farther into the distribution tail. than what you've observed. Okay, if the null hypothesis is true, it tells you how rare or strange your sample would be if the null hypothesis is true. Okay, it gives you the probability of seeing a larger statistic than what you've observed. And it is the proportion of times that you would wrongly reject your safe null if the test statistic you've observed is enough to lead you to adopt the alternative. Testing procedure is like choose a cutoff alpha for your p-value p. I said choose. Huh? Isn't that perfectly objective? Shouldn't the statistical test be perfectly objective? And then so that we would not have to say anything about it, and then just number tells everything? And the answer is no. 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 There is always a room for subjectivity to get in over there. Alpha threshold, okay? Critical value. Oh, the textbook told me to use alpha being 5% rule. Good luck with that, but that's not really the case. Argument has to be there. Okay? This is why the business communication is important as well. You have to be able and you have to be courageous enough to tell your boss and say alpha being 5% rule is not God written, the Bible written one, right? There is a room for argument. Alpha 5% may not be sufficient. You will have to go for 1%, or maybe 0.1%, or even stricter. That's the point of this lecture today. Okay? You have to be able to argue, right? You choose. Okay? And you have to be able to question, why did you choose alpha being 5%? And tackle those things. Okay? That will separate you from the rest of the group. Okay? Now, and conclude the significance and variable association for P being smaller than alpha. This is justified as giving only alpha probability of a false positive. For example, in regression, beta hat being not zero, only if its p-value is less than the accepted risk of a false discovery for each coefficient. Okay? Good. Well, our coding will be there, right? Online spending is there. Central limit theorem states that the average independent random variables become normally distributed, i.e. Gaussian, if your sample size is large enough. Okay? Sample statistic, okay? The mean kind of things will converge to Gaussian, okay? If you have large enough sample size. And the frequentist uncertainty is this idea, okay? If I was able to get a new sample observations, right, from the sample data generating process, what is the probability of distribution, probability distribution on the new sample average, right? New sample average. So depending on the sample that I get from the same, data generating process, right? What's the mean, right? The likelihood of having those kind of means, the average figures, or beta estimates. If I were resampling again and again and again, okay? What's the likelihood? What's the probability distribution of those betas, right? It will be like this. Well, if we go to R coding for this purpose, let's go over here, right? So to save our time, I'm going to stop a little bit and then restart again, okay? All right, so you start RStudio, and I just make it my habit to write the initial part of the code like this, so that I install those packages potentially necessary, right? Whatever package that we happen to learn in this course, I just accumulate those things and then that's just throw in over here and activate it using library command, okay? I don't know. This is my approach. You may like it or not, but set the work directory like this each time. And then here we're going to go through browser spending analysis in online spending activity for 10,000 households over a single year. And this is given by the textbook author. In addition to their total US dollar spending online, each row of the data set contains some basic information about a single household, such as whether they have any children, whether they have access to broadband internet, and their race and ethnicity and the region, right? So import browser data, and then check out this guy. Yeah, any children ID, and then broadband, whether you have it or not. You have it, 1 or not, 0. You have any children, 1 or not, 0. Kind of dummy variable, okay? Hispanic or not, that's ethnicity information a little bit. And the race, okay, is over here. And the region, that's Midwest, South, and Northeast kind of region in the US. And finally, the dollar amount of spending online, right? Okay, so data histogram. Okay, for first of all, let's draw a histogram of spending amount. Okay, I'm sorry here. Yeah, it looks like this. And the thing is, I took the log of it. Why? Because if I don't take the log, you will see it is a lot more what? Right skewed to the positive. That's why. And then basic statistic and row and browser number of observations will be there. And then the average amount spent will be shown like this on your screen, like this console screen. And then variance of sample mean, right? Variance of sample mean is this guy. Sample mean with variance divided by the number of observations over here. Because we are interested in the standard error of it, okay? Divided by the number of degrees of freedom, kind of things. Sample mean, and then standard error of the sample mean will look like this, okay? Mean, which is x bar, and XPSE should be your standard error of this x bar, right? So for that part, we do it again like square root of number of observations. We divide it like this, okay? Good. So you created these variables over here, x bar, XSE, right? I want to draw a normal distribution based on the sample mean and standard error. The domain of x would be almost centered around the mean that you found in 1946. And this central limit theorem states that the average of independent random variables becomes normally distributed if your sample size is large enough. So n is 10,000. Let's say this is large enough. And then the sample average for online spending is normally distributed with the mean of 1946 and standard deviation of 80. So we're going to create XX matrix or something. Where is it? Like vector, which is going to be a sequence from 1650 to 2250, which is centered, an interval that is centered around 1946. Okay, and then the length of this vector is 1000, which means chop it 1000. Okay, this interval, chop it 1000. Why? Because we are going to go draw a graph of x to y. X is chopped, 1000 observation will be there, and then for each x we're going to compute those normal distribution probability. Okay, then xx, I just show you over here, yes, and then we're going to plot that normal distribution curve, a beautiful bell curve like this. Okay, good. Now You see d norm, that's distribution function of normal distribution, x bar, the mean, and xse, the standard deviation. Yeah, like this. What is the distribution? It is our best guess at the sampling distribution, right? It captures the uncertainty described by the thought experiment. If I was able to get a new sample observations from the same data generating process, okay? The same economy, same country, like this, right? Same data generating process. What determines this online spending? We don't know, but maybe there is a data generating process that makes people to spend online somehow, and we are capturing with this data. So people's living is a kind of a data generating process itself. So another set of 10,000 people from the U.S. population, we obtain this kind of sample of online spending. Okay, what's the probability distribution of the sample mean? Okay, not that sample itself, but the mean of online spending. This is a frequentist uncertainty, right? So that's this distribution. Okay. Remember, I said before the distribution itself, distribution of the sample of online spending is right skewed, which is positively skewed, which is extreme positive will be there. Extreme amount of online spending is there, but those majority of them are clustered at lower level. Okay, but here the distribution is not right skewed. It's bell curve, symmetric, right? No skewness. Why? Because those highly skewed distribution is about the sample itself, the frequent, what's that? The distribution of the sample. What you see over here is not the sample, but the distribution of potential distribution of sample mean. This is sampling distribution. Okay, sample means. Okay. Now, for this part, well, the mean. Okay, if we were to extract the data in other setting, the same data generating process, but different sample, right? If we were able to obtain different samples from the same data generating process, would we get really the sample means like distributed like this? Okay, sample means, would it be distributed like this bell curve? Okay, that thought experiment will be done over here using bootstrap method. Bootstrap. Holy cow, I know. But this is based on the same sample over here, assuming that we are going to get the same, we're going to get the sample from the same data generating process, from the same US population, let's say. Okay, but we don't have US population data, but all we have is 10,000 people's data. So let's bootstrap it, which is repeated sampling based on this 10,000 observation, right? Some guys will be represented multiple times. Okay, let's allow for that kind of things. Same data generating process. Okay, resample with replacement, B times, we're going to do sampling like that. Okay, big B times, bootstrap. That's why. Calculate your estimate using this resampled set. Then the B number of estimates is approximation to the sampling distribution for the estimate you are interested in. So let's first get the sampling distribution of average online spending by bootstrapping 10,000 times. We will get the mean and standard deviation of the bootstrapped average of online spending to draw a smooth Gaussian distribution curve as a benchmark. Also, we will draw a histogram of the 10,000 bootstrapped sample average online spending. So we first of all assign 10,000 as big B, bootstrap it, and then and get the average of this, and then standard deviation of this, right? For 10,000 times, okay? And then standard deviation, and then the average is obtained. Now draw this, and you see the sampling distribution, okay? The curve is based on the bootstrapped sampling mean and its distribution. The bar chart is the histogram of those means, okay? Bootstrapped 10,000 times. Each time you're going to have samples and you're going to have means. Those means, 10,000 of means, you will have it, and then the distribution looks like this, which is awfully similar to bell curve, the normal distribution. That's what I'm trying to say, okay? So that's it. And then regression analysis, you can try it. Log of spending should be a function of broadband, and then any children kind of things, right? Right hand side variables. You see the result over here. If you have more, you have broadband access, of course you're gonna spend more in online. If you have children, you're gonna spend more on online because you're too busy to go to your shopping mall and then changing diapers and things like that. So you just do online shopping and then buy it. Anyway, non-parametric bootstrap is also there. We can bootstrap not just the sampling distribution of mean, but also regression coefficients, betas, those betas, and see possible distribution of betas, assuming the same data generating process. So let's bootstrap 1,000 times. Big B this time will be 1,000, and then we're gonna bootstrap those regressions, right? 1,000 times, and then what are those betas? How does it look like? Right, we show up, and then we're gonna see the correlation. You're gonna see 1,000 betas of what? Broadband, and then any children, okay? So betas, it's stacked up, and then we're gonna see some of these the correlation to see if these two the coefficients are correlated, okay? Two variables correlation can be nicely summarized, or it can be showing up in the form of correlation between these betas, two betas. You see over here, head betas, 6 betas are shown, okay? I said 1,000 times bootstrapping, regressing 1,000 times, okay? One time regression was difficult, but now you are doing it 1,000 times of bootstrapped sample, okay? For each bootstrapped sample, you run a regression, online spending against this broadband and any children, okay? And then first time, second time, third time, and all the way down to 6 times, like that. And you see the correlation coefficient between these two, which is minus 0.07. I say it's almost to 0, no relations, almost no relation, little correlation between these two, so we are safely moving on. The estimated spend broadband relationships roughly are independent from the estimated spend children relationships. To draw a histogram and the Gaussian distribution curve together, we first need to set the domain, which is from the minimum to maximum betas of broadband. We will split into 100 points like this, okay? Draw a Gaussian curve, and then it will look like this. Yes, and the histogram as well of that beta, okay? Broadband beta, okay? So what do we see? The distribution of 1,000 bootstrapped betas of broadband, okay? And you see that the distribution of beta looks like this: 0.55 seems like close to the mean of these bootstrapped betas. Okay, so if you think about the test, okay, if you think about the single regression that you did before, okay, that's a single regression that you did before, the online spending against this broadband coefficient, broadband, okay, broadband. Of course, there was any child, right? The beta coefficient over there, right? Is that beta coefficient significantly different from 0 or not? The Z statistic told us that it is awfully significantly different from 0. Okay? And this picture shows us visually that it is indeed away from 0 in a very, very significant manner. You see this beta, the center of beta, 0.55. And then where is 0? 0 is far away from here. So far away from here. Okay? That it does not even show up over here in this graph. Too far away. Way bigger than 0. That you can visually see, show it. Okay? That's what this is about. This is the histogram of possible betas of broadband variable. See how far it is from 0. The following is considering the multiplicative relations when you take the natural log of dependent variable. And I told you before, you can run regressions. By taking the log of dependent variable, but at that time, we have to consider the multiplicative relationship among these variables on your right-hand side, because we are taking the log of it, which means e to the power of these beta coefficients will be there, beta plus something something. So there will be a multiplicative relations. Okay, so let's get back to the lecture note 6. All right, here, yeah. From univariate regression to multiple regressions, okay, testing many variables is an issue, right? The problem of multiplicity, not multiplicative relation, but multiplicity, many variables, testing it simultaneously, right? You face similar problem, but even more. Alpha, right, that you saw before, false rejection rate, is about a single test. Okay, it's about a single test, single variable. If you repeat many tests about then about alpha times 100% of the null test should erroneously pop up as significant. You saw that before. Alpha is a false rejection rate, right? You're healthy, but still it rejects and you're thrown into hospital wrongly. Help me out! That's false rejection rate. Okay? Imagine you do this kind of things, right? For all different variables, right? And those variables, let's say, are all garbages. All of them does not have explanatory power. But with these statistics, it says that 5% time or alpha percent of time, you're going to find some significant result over there. So that 5% or alpha percent of garbages will show up as, I'm not garbage. That's the problem I'm talking about here. Okay, suppose that 5 of 100 regression coefficients are actually influential, not garbage, right? And that you find all of them significant. Fine. This time it's okay. The first bullet point, second bullet point, it's okay. No garbage recognized. Fine. The test rest of them. Test the rest of them. Test the rest of them, which means 95 variables left, column-wise, 95 variables. Test them at 5% significance level, or false rejection rate. Okay. since you reject H0, H null, for 5% of the useless 95 variables, you're going to have this kind of problem over here. 95 times 5% will show up as significant. I'm not garbage, even though they are garbage, right? That's 4.65 variables on average. They will show up as non-garbage. You divide this guy by 5 plus 95 times 5%, which is 5 is non-garbage variable plus those the garbage variable that is falsely identified as non-garbage. Okay, that's 9.65. So if you do the math, you will realize that 50%, almost 50% of those variables that you find significant in these 100 regressors, almost half of the regressors will be garbage. Okay. This is what we call a false discovery rate. Okay, significant tests are false. Since you reject H null for 5% of the time, 5% of the useless 95 variables, 50% of significant tests are false discoveries. Serious problem. Okay, in big data analysis. We call this false discovery proportion, FDP. And it can be really big with a small true non-null rate. In the previous example, let's say only 5 of 1000 regression coefficients are actually influential. Then the rest are garbage. You find all the 5 variables significant, test the rest of them at alpha 0.05, then 91% okay, of significant tests are false discoveries. Okay, so watch out. Okay, those garbages may show up as non-garbage, and then it will screw up your statistical inferences later on, right? So Zimbabwe inflation rate being significant predictor of S&P 500 may show up like this. Okay, may show up like this. If only one of 1000 variable is truly influential and the rest of the variables are garbage, you find the variables significant. Test the rest of them at alpha 5%. What is the FTP of the test? i.e., what is the chance that the significant relation you found in the multiple regression is false? Well, for this part, look at page 31 in the textbook. False discovery rate, okay, is defined like this. Okay, big data is about making many tough decisions. Instead of focusing on single test, we'll consider FD proportion like this: number of false positive divided by number of tests called significant. Okay, false discovery proportion. FDP is the property of our fitted model. We can't know it, but we can control its expectation. False discovery rate, okay, is nothing but the expected value or average of FDP. It is the multivariate aggregate analog of alpha, false rejection rate, okay, FRR, right? Okay. False discovery rate. So this gives us to the answer to this question. If you are running regressions many times using big, some data, right? Or you find correlations and association of the dependent variable and this variable, that variable, that variable, that variable. Single variable alpha test gives us that, oh, this is significant. But in a setting, like a set of variables, right? How reliable is it? Okay, is there any kind of multiple regression analog of alpha? Okay, that's FDR. Okay, FDR. P sub k, false discovery rate control, it works like this. Here I give you a definition of order statistic. This is essentially a rank number, or the order statistic. The k, p sub k, okay, parenthesis k, This is the kth order statistic of P, so that P sub parenthesis 1 should be the minimum of this, right? Rank minimum value, okay? Minimum value, not just the rank, but the value of it in the minimum, and then the maximum should be P sub parenthesis n, okay? That's the definition of order statistic. Now, suppose we want to be sure that FDR is less than or equal to Q, let's say 10% this time, 0.1. The Benjamini Hochberg algorithm works like this. Rank your p-values of n variables from smallest to the largest. So minimum to maximum, p1 to pn over there. Set the p-value cutoff as p star, okay? So P star should be equal to maximum of P sub K, okay? The order statistics, okay? You order that, the P value of your many regressors, you can order that, okay? And then order statistic is over there of the P value. This P value, okay, the P value of Kth order statistics P value should be less than or equal to. It has to be less than or equal to because the p-value have to be smaller, right? The p-value has to be smaller than this ugly term over here, which is k times q over n. K is your order number, right? Rank number. How big is it? How, starting from the minimum, how small is it? Okay, the smallest kth explanatory variable in terms of p-value, starting from the minimum p-value, and you'll have bigger p-valued variable, bigger p-valued variable, bigger p-value, and then the case bigger p-valued variable, right, is there. That p-value is this guy. That p-value has to be smaller than or equal to q over n times k, okay? Why is this the case? Don't ask me, it's out of the scope of this class. The proof will be provided in this slide, so go ahead and enjoy if you're a mathematician, okay? Q divided by n, if n is big, okay? And then remember Q, we assumed it to be 0.1 over here, will be, the Q over n will be awfully small number, and then times K, will be increasing it to a certain degree. But P will be very small if N is big enough, right? K is a rank number. K should be your x-axis, right? So we're going to draw a XY chart like this. So the K should be on your X variable, right? Minimum will be over here. Maximum will be over there on the right-hand side. And then you can draw a straight line as a cutoff line. You can draw a straight line like this. Based on this, Q over N will be your slope. Q over N will be your slope, and K is your X variable over here. So that it increases like this, very slow manner. And then the P-value will be your Y-axis. So that the P-value for each variable will be plotted somewhere at some point that it will go above it, so that you cut off at certain level and then say, oh, these variables are something we should take as non-garbage, and the others, garbage, throw out. You can decide it this way. That's the Benjamini Hochberg algorithm. Okay. BH cutoff line for n equals 9, and then Q equals what? 0.1. Then the slope should be like 0.1 divided by 9 like this. So that these variables over here should be significant, and then these variables over here should be treated as garbages, right? Proof of BH algorithm, out of scope. I told you, yeah, go ahead and read it in your free time. Yeah, Yes. And then FDR roundup, we introduced the problem of multiplicity by saying that a given alpha I mean, can lead to a big FDR, right? And then BH reverse the relationship. It's recipe for the alpha of Q that will give you whatever FDR Q you want, right? FDR is the way to summarize the risk when you have many tests, the danger that you have. When you have many tests, you will never think about the testing the same again, right? So, alpha. All right, all there is to know about FDR, p-values from the null distribution are uniform, and p-values, right? Null distribution, 0, and then there has to be some uniform distribution, and n of them ranked. The p-values, by the way, why should it be a uniform distribution? Because null hypothesis, right? Null hypothesis says that what? All your explanatory variables in your regressions are garbages. That's null hypothesis, right? The p-value should be what? 1 for all variables. Like it has to be 1, 1, 1, 1, 1, 1, 1, 1, 1. Nothing can explain your dependent variables. That's why the p-values has to be uniform distribution. 0 to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, right? And n of them ranked and plotted should lie along a line with a slope of 1 over n. And then FDP is the number of false discoveries divided by the number of test results called significant. You don't know the FDP. You can control FDP, which is expected value of FDP, to be less than or equal to Q, right? Among n tests, so that rank and plot p-values against the rank over n, and draw a line with the slope Q equals n, and find the max point where p-values cross the line, and use that point to set your rejection region. That's the idea of algorithm. Quitting R usually have the script, not the workplace. The workspace is the save this right RDA image, while the R script just text. Stay up to date. Make sure you have latest version. Stay organized. Keep track of your work. Keep things simple and don't panic. Google search a lot, right? Google search, Naver search, whatever code. What is this code about? Like error messages. Go ahead and find it. Better answer than me, actually. Honestly speaking, right? I told you. Consider using shared drives to collaborate, or even better, create a group GitHub repo and repository, and use version control. R is a fantastic tool, and there is tons you can do, but don't worry about learning everything right away. Plenty of resources out there. Yeah, things like that. Okay, so for this part, if we go back to R over here, okay, now want to use the false discovery rate, a discussion in Benjamini Hochberg. There we want to run a regression, and summary will be there. Yes, over here. Yes, and then round. Yes, round means what? Rounding up at 2 digits below decimal points. Now, first obtain the regression results, coefficients, etc., and keep it as a matrix. Results should be a matrix of the summary table, right? And then the p-value, okay, is created, right, as a vector. So results, where's that results? Yeah, right. Reg results should be over here. right? You see this, right? Now we have the coefficients and t statistic or z statistic interchangeably. I'm going to say it, so don't worry about it. P value is over here. All right, and then we want to draw a plot, okay? Plot of this p value, and then this Benjamini Hochberg algorithm based line like this, like this. Okay, so that's that. Okay. Oh, did I say n as a number of observations? No, n as the number of variables. I'm sorry. Sorry about that miscommunication. The n has to be the number of variables that you throw in your regression. That's 9 over here because we have 9 variables thrown out. Okay, in this reg results, if you see it. Okay, so that's that. The line has a slope of 0.1 over 9, which corresponds to the BH coefficient line, n of 9, and then Q of 0.1. The recipe is that find the largest p-value that is below this line, and call it what is it? These initial 1, 2, 3, 4, 5 variables are significant ones in terms of p-value. 1, 2, 3 above this threshold line, these variables are garbages. So if you look at these results, the reg results, go ahead and identify 1, 2, 3, 4, 5 variables that has lowest p-value. Okay, that's this guy, that guy, and then that guy, that guy. Is that right? Yeah, minus 0.04 means like you have at least 3 zeros below decimal points, and then you have 5 over there, right? And then so 1, 2, 3, 4, 5. These variables, any children, broadband, the Hispanic, and then region and region the west. We exclude the intercept in this analysis, right? That's it. So that's how we use this Benjamini Hochberg algorithm. All right. Okay. Right. So these are our textbooks, figure 1.10 and 1.11. Yeah, uniform distribution. So interval 0 to 1, and the probability of each having the variable is probability 1. So uniform distribution, and then yeah, like this, and then you go ahead and match with the textbook figures over there, right? So we'll move down to model selection, right? Thanks for watching.